Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we begin our study of lasers. First, we will discuss a few principles of lasers which are applicable to different kinds of lasers. Okay. So, we do not really need to worry what is the actual laser that we are studying, because these general principles are valid for all the different type of lasers. The reason why we want to study these principles is because you will be using these principles in studying various lasers. Okay. To study each laser would probably take a course of its own, since our objective would not be satisfied with that one or would be served by that kind of an approach. What we do is we will give you basic ideas of lasers, which you can then if you desire so, or if the need arises, you can apply to different lasers, as you know. Of course, that is the first point. The second point is that by studying these basics of the lasers, then you will be able to better appreciate the semiconductor lasers, which is the workhorse of optical fiber communication systems. Okay. There, once we go to semiconductor lasers, study of semiconductor lasers, we will be employing most of the terminology techniques that you would study in this module and perhaps in the next module, and at that time you do not have to go and relearn all these basic things. And the third point why we would like to study these laser basics is because there is an intimate connection between a laser and an amplifier. Okay. In fact, the connection between them is so interesting that all lasers in themselves will employ an amplifier. So, there is an amplifier inside a laser, okay, and then you enclose this amplifier by a certain thing called as cavity. Okay. So, you actually make a cavity, okay, which is usually bounded on all sides, but of course, if you bound everything and then put the amplifier inside, then you will not be able to get light out. Okay. So, this cavity is usually formed with mirrors, which such a way that one of them is very nearly reflecting. Okay. So, any radiation that comes would be just reflected back, whereas the other one would still be reflecting, but it would only be about say 99%. Okay. So, that 1% of light that comes out from these lasers is sufficient for us to actually work with it. Okay. Of course, the numbers 99 and 1% are not to be taken in this manner, because some lasers actually work with 90% and 10%, some of them work with 65% and 35%. So, depending on different lasers and depending on how much power you want, you can adjust this output coupling ratio. Okay. But nevertheless, every laser has three main components. The first component is an amplifier, because without an amplifier you cannot have a laser, but having an amplifier is quite different from having a laser. Okay. So, to go with the amplifier, you also need to enclose this amplifier in a enclosure, and that enclosure is what you do by having these mirrors, so that light cannot escape, but has instead forced to go into the amplifier by these cavity mirrors. And third and most important component of a laser is what is called as a pump source, okay, or what we call as a pump. What is a pump and what is the amplifier made out of? We are going to start looking at that one. But if you now just look at this picture, which actually is a laser, okay, most lasers have these three components, and then you take away the mirrors, okay, and in addition to that retain the pump and the amplifier, but now supply weak signals from the outside. So, this is the optical signal that I am sending in, okay, and what you would get would be a amplified optical output. Okay. So, in that case, this is acting like a simple amplifier. In fact, the ideas of amplifier, the ideas of oscillators, lasers is essentially an oscillator, is not something new. You have already studied this in your electronic circuits. So, you have studied perhaps Hartley oscillator, Colpitt's oscillator, and if you look at the circuit diagram of those oscillators, you would find that there is an amplifier, okay, and there is a pumping source. The pumping source or the external energy is coming from the DC power supplies that you are going to connect to the amplifier. So, if you are going to implement this Hartley or Colpitt's oscillator using a bipolar junction transistor, then you connect the connector to certain VCC and collect the emitter to VEE, and this VCC VEE supplies are DC signals that are coming in, and it is this DC energy that will be converted into AC energy when you complete a amplifier or convert an amplifier by putting in a feedback circuit, right, and convert an amplifier into an oscillator. And this cavity mirrors that I talked to you about does exactly the same kind of a job that a typical phase shift network or a feedback network in a Hartley or Colpitts oscillator does. Okay. So, going from amplifier oscillator, there is a huge connection between the two. In fact, all lasers essentially are amplifiers or include amplifiers, but their radiation is self sustaining, their oscillations are self sustaining once the initial transition period or the transient period is finished. Okay. So, we are going to study these lasers, but I am not going to go very deep into the mathematics. I will leave lot of these steps as exercises for you. These steps are not very hard, they just involve combining a few equations and then substituting one into the other. But when you do that, you will realize how simple the initial ideas of lasers are. But of course, it is not just these ideas or mathematics that is important, but to actually build these lasers, fabricate these lasers and get them to market is the most challenging aspect. Unfortunately, this is a course on physics, technology and other things, not a course on how to fabricate and then get it out onto the market. So, since that is not the purpose, we are not going to look at that aspect. We are of course going to look at the detailed theory behind these lasers and what takes it to components, or what components are required to make a good laser is what we are going to study. Okay. Now, before we can jump in and start studying semiconductor lasers or in general any laser, we need to study a little bit or recall few topics from black body radiation. So, what is this black body radiation that I keep talking about? Well, if you take a cavity, okay, and you take this cavity and heat it up at a temperature T, then it can be shown that this cavity would emit radiation. Okay. This is something that you would have studied in your physics. Okay. Every material which is at a temperature T, where T is the characteristic temperature of the black body, would emit radiation, and of course, the body can actually absorb radiation at the same frequency range and as it would emit. Okay. So, the radiation emitted from a black body, which is essentially just a nice manner to talk about a completely closed enclosure. Of course, you will not have a completely closed enclosure, there will be a small hole in this cavity. Okay. So, that radiation can be actually emitted from that, although schematically I have shown that this is emitting light everywhere, but actually it will be light will be emitted by this small hole that is necessary to draw out the radiation, and this black body is characterized purely by its temperature. Okay. No other consideration is necessary. So, you may have a cavity in this manner or you may have a cavity in this manner, okay, with a small hole, as I said, okay, of the same nature. Then if both cavities are at the same temperature T, then the radiation emitted by these two bodies will be identical, okay, and the radiation that is emitted, we call this as rho f delta f, where rho f delta f corresponds to energy density between the frequency f and f plus delta f, or the energy that is emitted in that region is given by Hf, which is the energy of the photons that are emitted from this region, times the photon density, that is the number of photons between the frequencies f and f plus delta f, which we will call by phi f df. So, phi f df is the photon density in the frequency range f to f plus delta f, and Hf is the energy of the photons. The product of these two is the total energy density. Okay. This is the energy density that we are talking about, and this, as I told you, is a characteristic completely of the black body temperature itself. Of course, this radiation is given by a nice equation, which I will write it down. It is 8 pi by c cube Hf cube df, df is the frequency interval that I am considering, divided by e to the power Hf by kT minus 1. Okay. You might ask, what are these different variables? C is something that you know, C is the velocity of light in free space, and it has a value of 3 into 10 to the power 8 meter per second. H is the Planck's constant, okay, and this Planck's constant is a very small but finite number. Okay. H is about 6.626 into 10 to the power minus 34. I think the units of this one are joule second. Okay. And this Planck's constant implies that this radiation that is coming out is actually quantized radiation. The history of this quantized radiation is something that we do not want to go, but some names like Rayleigh's law or Rayleigh-Jean's law, and then other thing, Wein's displacement law, all those things are associated with the same thing that Max Planck worked on, and his ideas of radiation quantization have led to the development of quantum mechanics as something that you already know from your 10th or 11th and 12th class physics, okay, or maybe in your engineering first year as well. But the important point to note here is that this formula, the radiation formula as given by Planck, okay, involves C, which is a constant, H, which is a constant. Of course, frequency range is defined by whatever the frequency range that you want, and then you have e to the power hf by kT minus 1. So, this term if you see is dependent only on f and t. Okay. Now, this is the black body formula, and please keep this particular formula in mind. We are going to use this formula later on, but now let us go back to something else. Black body radiation, as we talked about, is a specific property of the matter, okay. But if you look at what the matter is, right, matter consists of these atoms, and these atoms typically have these energies, okay. However, in matter there will be different energy levels or energy bands, okay. We will talk about energy bands later on, but intuitively if you think of a single isolated hydrogen atom, for example, then the level n equal to 1 will have a certain energy, then n equal to 2 will have a certain other energy, and so on. Okay. Similarly, when you talk of matter, instead of single isolated energy or energy levels, you will have isolated energy bands. So, you will have a band of energy, we will call this as E1, then the next band of allowed energies we will call as E2, and the next band of allowed energy levels we will call as E3, so on and so forth. Okay. So, this concept of matter having these different energy levels should be something familiar to you from your simple hydrogen atom kind of a study. Okay. So, keep that in mind, and to simplify our analysis, instead of considering bands, I am going to consider discrete energy levels. I am going to assume that we have these discrete energy levels, okay, and call these energy levels as E1, E2 and so on. Okay. For now, we will simply consider only 2 energy levels, which is typical that we would be studying, and the difference between the 2 energy levels we will denote it, or we will give it by E2 minus E1. Okay. A crude analogy I want to show here is, you can see this one. I have a house, okay, or someone has a house, and there is a party going on, and there are a lot of these people attending the party. Okay. So, you have certain population in the ground floor because the party is being held in the ground floor, and in the normal condition of this party, everyone is occupying the ground floor. Okay. So, there is a certain occupation density, or the number of people occupying this particular floor. Then, since this floor corresponds to a certain energy, we have called it as E1, and this people occupying this, the density will be denoted by N1, and you would see that the energy level N1, or at the energy level E1, the population density N1 is quite high, almost everyone is in the energy level N1. But suppose and now if you look at the population of people at the energy level E2, and population of energy level E2 means that you are talking now about first floor. Okay. When the temperature is 0, then there will be no people at the top. So, you can, in the analogy wise, imagine that no one has an energy to climb the stairs and then go to the first floor, and that would happen in the matter condition when the matter is kept at temperature T equal to 0. So, most of the energy levels are, or the energy most of the population is actually filled, or in fact all of the population is filled and existing only at the ground level energy, which we have called as E1. Okay. Now, suppose that we are now at a higher temperature which means that there is some some music or something that has been turned on in the first floor, and there will be some people who are actually who like music, and what they will do is that they will climb up the stairs. Okay, so these are my stairs, very crude manner, okay, and they will actually go into the first floor. Okay. We call them as excited atom in the matter kind of a thing. So, in the matter, when there is non-zero temperature, then there will be certain energy associated or certain energy available to the atoms which are sitting in the ground floor, okay, and these atoms can absorb that energy. Usually it is electrons which would absorb this energy, and these electrons would then jump to the next available electronic level or the energy level. Okay, I am assuming since there are only 2 energy levels, they can go from E1 to E2, right. So, in the party scenario, this is analogous to someone being excited by the presence of music or a DJ and then taking the steps to go from lower or the ground floor to the first floor and enjoy the music out there. Okay. But when a person leaves from the ground floor to the first floor, they would have created an empty or a vacant space in the ground floor, and this empty or vacant space in the ground floor is what we call as a hole. Okay. So, hole has been left. Now, suppose the host of the party brings some interesting food here from the left hand side. Okay. So, maybe this would be some potato chips that are brought in, and what would happen? People are hungry and each of them would start walking towards the food. Okay. So, people would line up to get the food. So, here are people lining up in the direction of the food, and because there was a space here, I have kept the space as it is. Okay. And of course, you still have a first floor where one person is definitely enjoying music, not caring about the chips. Okay. So, what you have actually seen is a very interesting phenomena. The person here, okay, moves to the left and then starts eating the chips, because he cannot move, or the person, she cannot move to the left anymore. But the idea is that as the person moves to the left, the empty or vacant space has moved to the right. So, you can see that the vacant space or the hole has been moved to the rightmost corner of the ground floor. Okay. And this can be thought of. So, instead of keeping track of people moving to the left, you can keep track of the vacant spaces moving to the right. Okay. Now, in ordinary matter, when the matter is at a temperature T greater than 0, the only way the electrons in the ground energy state can move to the next available energy state is by absorbing this kinetic energy that is obtained from the non-zero temperature, and the amount is kT. Okay. But let us say once this person has moved up, okay, he or she cannot always remain at the first floor and would occasionally want to drop back to the ground floor, because maybe they also like the food, or maybe they just got bored, or maybe they just exhausted all of the energy, they would like to just jump back to the first floor, and when they do so, they are going to combine usually into the hole, right. Of course, they have to combine with the hole because they cannot land on a person's head. Okay. So, what they will actually do is to land on the hole, and then what we say is that they have recombined. Okay. So, in the same manner, in an ordinary matter, electrons will be mostly located in the ground level with an energy level E1 with a population density N1. At energy level E2, the population will be sparsely present, because whatever the energy that is there has to come only from kT, unless you send out external energy. So, you send in external energy in whatever form, okay, usually in the form of electrical signals or in the form of another optical signal, causing the electrons in the ground floor to excite into the next available, or ground state to the next available energy state. Okay. And of course, the excited electrons cannot remain continuously there, they will drop back after a certain characteristic time. Okay. This characteristic time and energy are actually related by Heisenberg's uncertainty principle, which means that if we know the excited energy, or if we have excited the electron into the next available energy slot, then because we can predict the energy of that electron, okay, the time at which it stays in that position will become uncertain, and there is a characteristic time scale after which the electron spontaneously drops back to the ground state or the ground energy state. Okay. So, there are two kinds of things that are happening, right. So, one is that there is a pumping going on this pumping causes or gives certain amount of energy to the electrons in the ground state, which will then allow the electrons to go from the ground state energy E1 to the next energy state E2, and once they have reached the energy state E2, they will not linger on there forever, they will actually start falling off to the ground state, and after a certain characteristic time, okay, and that falling off on their own is called as spontaneous emission. Okay. So, this is called as spontaneous emission. Okay. There is also another way in which these excited electrons can fall down is when a certain photon or certain optical packet arrives or photon arrives, let us say, of the energy which is just sufficient for the excited electron to actually drop down. So, it is kind of going there and then saying, hey my friend, why do not you drop down, okay. And when it does so, okay, you will actually get two photons, one because the atom has moved from energy state E2 back to the energy state E1, that is, it has combined into the vacant hole here, okay, which releases one photon, and there was already an original photon here which was initiating this interaction, which does not get absorbed, it remains as it is. Its only goal or its only effect is to nudge the excited electron, so that the excited electron can actually go down to the ground state and then recombine and generate another photon. And you can imagine that if the number of excited electrons in the level 2 are much higher than the number of electrons in the ground level, then one or two photons that are incident are sufficient to drop a large number of electrons from E2 to E1, generating a large number of photons. Okay. So, with very few photons to begin with, which could come from noise in the system or externally indicated, then you can actually build up to an extremely large optical power at the output of the laser. Okay. And we should of course have certain materials with certain energy gaps E2 minus E1, which will be in the particular wavelength range, as we will talk about it in the next class, okay, or in the next module, so that this stimulated emission can happen in the wavelength range that we want, okay, and we should have the ability to pump the electrons which are usually occupying the ground state onto the excited state. So, which means that in the party analogy, we should have a music or a DJ music in such a way that most of them would like to be excited onto the first floor and very few people would be allowed in the ground floor. And when most of them actually excite and go to the first floor, and then when something else happens like potato chips are brought in, then people will drop from the first floor to the ground floor, and then one or two chips is sufficient for many people to drop down and then generate photons which will then be amplified. So, you start off with one or two noise photons, and at the output of the laser you have this huge number of photons coming out, and this can be sustained by having this feedback mechanism. So, people once they have dropped down, you again excite them by nice music. So, in the matter case, once the pump has taken the electrons in the ground state and excited them to the next available state, you again and again excite. So, the atoms which fall down are continuously excited back into the state, and you should essentially create a situation where the number of atoms in the energy level E2 or the excited state electrons, their density is much larger than the density in the ground state. Okay. Normally, ground state is the one that is completely filled or mostly filled, and the population at the energy level E2 will be very sparse. Okay. When the temperature is non-zero, there is a certain relationship which will allow you to tell how much would be the population density that one can expect in the energy level N2, and you can see that the energy level N2 will be something like N1 e to the power minus E2 minus E1 divided by kT. So, if you have sufficient energy kT, then you can still see that N2 would normally, this is under the simple equilibrium, no pumping. So, what would be the condition is that N2 will be sparsely populated, but when you pump and then excite, then it is possible for you to create a situation where N2 will be greater than N1, okay, or the difference N2 minus N1 will be greater than 0. We denote this difference N2 minus N1 by delta n and call this delta n as the population inversion. Inversion means inversion, right. So, you had most of the electrons in the ground state, but after pumping most of the electrons have been pushed into the higher order or higher energy state, and if they sustain there for some time, when you actually put some noise photons here, then they would all drop down and generate a stimulated emission, and then you can sustain the stimulated emission by taking this light which is coming out of the laser or the amplifying medium and then pushing it back via the mirror feedback, right. So, you have these cavity mirrors which will then take these photons and then push them back. So, repeatedly this light goes back, gets amplified, goes back, gets amplified, sustains itself and essentially comes out as a stimulated emission of radiation. Okay. So, in the normal unpumped case, there is only thermal energy which is available for the electrons. They would go to their higher energy state, but then they would drop down after a certain time by what is called as spontaneous emission. This spontaneous emission results in a photon, but many such spontaneous emissions do not give you a sustained radiation, and spontaneous emission by itself does not give you lasers. However, spontaneous emission is very important in a light source called as light emitting diode, because in a light emitting diode there is no feedback, there is no sustained stimulated emission. All of the light that comes out is because of the spontaneous emission, and we can show that spontaneous emitted light will be highly incoherent. Therefore, it has a wide spectral range and suitable only for low data rate optical communication applications. Okay. We are still not done with the laser basics. What we will now do is to write down certain equations for N1, N2, and we will see that only 2 level systems will not, we will not show that, but we will tell you that only 2 level energy systems cannot sustain lasers, or lasing is not possible. So, you need another level, a third level. So, materials with 3 levels at least for a laser to work. Okay. Of course, in practice you will also have more than 3 levels, you will also have 4 level lasers, but for majority of the lasers that we are interested, we can approximate our material, amplifying material, as having 3 energy states, E1, E2 and E3. In the equilibrium case, the population density will be like N1 much higher than N2, which is much higher than N3. But once the inversion has happened, N2 will be much higher than N1 and N1 will be much higher than N3. How do we bring this about? What are the conditions? What is the pumping rate that is necessary? And once that pumping rate is achieved, what happens to delta N? All that relationship is what we are going to study in the next module. Thank you very much.